Hello everyone. In this video, I'm going to do two examples to show the Taylor polynomial approximation. You've seen Taylor polynomial approximation or the series in calculus. And if you remember that formula where you set it up as a summation. And it is one of the best numerical approximation for functions near a particular point, let's say x naught. And of course, if you review, you can check again this formula. Then you can see how you set it up, let's say, to approximate functions, let's say exponential function e to the x. And if you do the first term, you find 1, and if you do the P naught, naught or P sub 0 of x, you find 1. And if you do P sub 1 of x, you find 1 plus x, which means as you get these terms, the approximation gets better. All right. So that's kind of just to remind you what it is. But really for us, when it comes to this topic, we're going to connect these approximation scheme to the solution of differential equation. So we're going to look at the differential equation, kind of construct the Taylor polynomial for its solution. That's what we will do. And the initial conditions will be built in, so it'll be initial value problem. And I'll show you the two examples that show the method that behind using this Taylor polynomial approximation to solve this initial value problem. So let's do the first one. And this kind of just make it an easier version and determine the first three non-zero terms in the Taylor polynomial approximation for the given initial value problem. So here we're looking, of course, for some solution y of t, right? But it's going to be described as a polynomial. And more terms you find, the better fit this solution is, right? So that's what you've seen in the past. But here, just the request is just approximate to three non-zero terms. So we're given already the kind of like the first one here. So let's see what's the second one. Y prime of 0, just substitute here directly. X is 0 plus 2 y of 0 squared. So that's 0 plus 2 y of 0 is given, which is 1 squared, so it's 2. To go into this polynomial, we need the second thing, and I'll give you the formula. So if you haven't looked at this before, these examples, I'll give you the formula or the construct to it. But let's say, so here, look at y of 0 is 1, so it's not 0, so we can say this is 1, 1, we need 2. Y prime of 0 gives us 2, so that's 2. We need the third one, so we need to find y double prime. Y double prime, we're going to find it from here, and so this is 4x plus 4y prime. All right, so what is y double prime of 0? It's 4 times 0 plus what is 4 y prime of 0? Y prime of 0 we found to be 2. right? So it's 8. So y double prime of 0 equal 8, and this is 3, or the third one. So if you haven't looked, what is the general construct to these solutions using the Taylor polynomial? It is this polynomial. Here the independent variable is x, is going to be the y of 0 plus the first derivative evaluated at 0 times x plus second derivative evaluated at 0 over 2 prime, right? And now if you look at it before, you remember what it is. And we did it at one point as well in this course when we wanted to derive like Euler formula and stuff. So the general kind of like how the terms are going is the n derivative evaluated at 0 over n factorial times x to the n. All right, so now we can go back and just say, all right, what we're looking for is y of t. Y of 0 is 1 plus y prime of 0 is 2 times x plus y double prime of 0 is 8 over 2 prime times x squared. Since I don't have zeros as a factor and canceling these terms, that's the first 3 I need. So the approximated solution using these 3 non-zero terms is going to be this. Okay, so let's do one that's a little bit more involving, because this has just linear from the first degree there, and you have one initial condition. So let's do another one. This is a similar question. We need to find the solution to this using this Taylor polynomial approximation solution, and it is an initial value problem. And here we don't have y, so it's okay. We don't need to get confused with it. It just means that x is like the y here in previous example, and the t is the x, right? So that's kind of how you look at it. So the t is x of t, right? So what we need to do? So I need 3 terms, which means if I get a term that has only 0, I need to keep going until I collect 3 non-zero terms. So let's, the first one is kind of given here, x of 0 is 1. So that's 1. All right. X prime of 0 equals 0. We know in the formula it's going to cancel everything, so that's not a 2. All right, so let's find the x double prime. So this formula, instead y double prime is going to be x double prime. So if you want to mimic this, I'll show you here. So for next example, which is the one we're working on now, you're going to say p of n of x, which is now is going to be t. What you're looking for is x of 0 plus x prime of 0 times t. plus x double prime of 0 over 2 factorial times t squared plus x double 3 prime there of 0 over 3 factorial times t cubed, and so forth. So the nth derivative here, x at 0 over n factorial and t power n. So that's for this example. Okay, so let's look into x double prime. I have x double prime here, so I'll just solve for it. So let's just solve for it. X double prime equal negative 2x divided by 2, which is negative tx. So x double prime of 0 is just going to be negative 0 times x of 0. X of 0 is 1. So this is x of 0. So it's 0, so this is not useful. All right, so we need to keep going then. The third derivative. Now I need to differentiate this. And remember, this is a product, so that we need a product rule. So it's going to be t prime, which is 1, times x, plus t times x prime. All right, so x plus tx prime. And now that means we can find the value of this third derivative at 0. X is 0 is x of 0 is 1, right? So here, let's show it. X of 0 is going to be here 1. What else? Plus t times x prime of 0. Let's do it here. X prime of 0 it's given as 0, right? Yeah. So for this third value, we get negative 1. All right, so yeah, so this is not 0, which means this is 2. And now we need the third one. All right, keep going. The fourth derivative, we're going to differentiate this. Right, so it's going to be negative. X is going to be x prime. Product rule there again. X prime plus the x double prime. So negative 2x prime plus the x double prime. All right, so we're ready to figure out what is the value of the fourth derivative at 0. Yeah, x prime of 0 is 0, this one. X double prime of 0, we found it here to be 0. So this is 0, so that's not useful. All right, keep going. Similar way, let's see if I can shorten it here. It's the first one will give us that. Then the product rule is going to show up and give us these terms. Then it's 3x double prime plus t times x triple prime. All right, so what is the fifth derivative at 0? X double prime is, we found is 0. x triple prime is 0, but t is 0, right? So t is 0. So when you plug that in, it's just 0. So, all right, not useful. Keep going. So negative, we'll do the here. So 3 times third derivative there, plus now product rule on this, t prime is 1, so x um, triple third derivative there, plus t times the fourth derivative. Let's combine 4 times the third derivative plus t times the fourth derivative. So let's do the evaluation at 0. The third derivative is what? Is negative 1 we found. And 0 times the fourth derivative, doesn't matter what it is, it's just going to be 0. So this is a 4. All right, that's 3 for a third one. Now I'm ready to go back to what I mentioned here, which is the good thing with this, you've seen this, so you know the concept of Taylor series here, and we just apply it to this differential equation to construct the solution based on how much uh, kind of precision we want. All right, so since this is it's built in x, right? So the solution is going to be x of t is 1 minus, show you here, for the third one is negative 1, so plus it being negative 1 over 3 factorial, which is a 6 times t cubed. And we don't have any until we get to the sixth one. So the sixth one, we have a positive 4 over 6 factorial, t to the sixth. So x of t is 1 minus 1/6 t cubed. And that's gonna be 720, and 4 by 720, it's gonna be, I think, 1 over 180 t to the sixth. So you can see it's a little bit involving, but it's still a nice different way. It's a practical way which also can be programmed in approximating the solution of this differential equation using the Taylor polynomial approximation. All right. And that's kind of the method in this introduction. Thank you.